Callum and I was graphic designer and coder.
Hi, I'm Matthew.
And I'm Jack.
And we are the engineering technicians of the team.
Hi, I'm Heather.
Hi, I'm Zach and we're the physics research and development team.
Hi, I'm Nafisa and I'm the project manager.
Together we are TIKOS. Welcome to our journey.
As we embarked on our industrial cadets journey, we were provided by an 8-year brief by our mentors at TALIS. This brief stated that we were to devise a system to transport several thermal military imagers across their floors in their Glasgow site. This brief set out with specific requirements that we had to tackle. Our requirements were to be sustainable and long-term. However, our team quickly gathered that there were a lot of obstacles in the way. One of these obstacles was that we could not use Bluetooth with our method of transport, and another one was that we had to travel through a clean room. This meant that our team would have to take extensive measures to ensure the quality of our product is high, as well as preventing any interference with the TALIS flows. Following this, we constructed a feedstock mind map and delegated our research areas such as materials, sustainability and existing solutions. After this, we collated it on A3 sheets of paper and produced real-life solutions.
Thanks, Matthew. As we got an understanding of what was expected as a solution, we got right down into the brainstorming sessions. These were essentially meetings which whenever idea came to mind, approaching this with the mindset that no idea was a stupid idea. So as you can imagine, we got some crazy ones. Taking the general gist of these ideas, we decided to split up and produce some individual initial ideas. As we took this time to separately understand the brief and viable solutions, we began to understand the ease teamwork provided in a team. As we finished our ideas, we revealed them to our mentors in many one-on-one presentations, from which we chose the idea which would be most preferred and suited to the company. We went forward with this idea and developed it to integrate some components we thought would amplify the solution, like a modular robot to make it mobile, maglev to prevent contamination, etc. The final solution, as can be seen on this refinement page, contains both the company's preferences and our own innovations.
Now, on to explaining our final solution. As you can see here, we divided our final solution into 4 components: the base, the dome lid and encasement, the metal alloy box for the Sophie light, the actual goggles to go into, and the maglev box. The encasement consists of 1D, a customized dome that sits on top of a cylindrical encasement. This part is made of HDPE, which is high-density polyethylene, which is a recyclable and very durable plastic, and it is actually one of the most eco-friendly plastics that is used in the industry. Sandwiched between these is a impact-resistant slotting made of styrene butadiene rubber. This material is cheap and easily sourced and offers great abrasion resistance and impact strength. As shown on the screen, the rubber gets slotted on and glued to the cylindrical encasement, allowing the lid to be closed without worry of harming the plastic. To lift and close the lid, a wide plastic handle, 1C, using anthropometric data is constructed and attached to the dome. A rounded pivot butt hinge, 1A, made of steel, is there to connect the 2 encasements together. Moving on to the base component, component 4. This is made up of 2 parts: a pre-made manufactured robot from RoboSavvy 4A, which slots into a circular, customized 3D printed impact resistor 4B, made of PC, polycarbonate. We chose to go for a pre-made robot as it allowed us to not only optimize our time as we spent it on refining the rest of the product, but also to turn our solution into a modular one, as it had 2 longitudinal protuberances on top, onto which our modified maglev boxes could be slotted on. The robot also had built-in sensors which would aid in increasing the solution's health and safety precautions. The impact resistor had a slight protrusion at the bottom, allowing the cylindrical encasement to sit on top and be glued on there. Going back to PC. PC is a high durable plastic that can be, as mentioned before, 3D printed. Another thing to note is that it is 250 times stronger than glass, which means that the robot will have no outside disturbances. It is also available in opaque or translucent, allowing the clear aesthetic of the product to be carried throughout. Now for the coolest part, component 3, our magnetic levitation box. This component was introduced and designed to minimize and prevent any contamination of dust particles on the goggles as they were to be transported into a clean room. The actual box, 3A, is made of a magnesium alloy due to its lightweight and contains the electromagnetic component 3C. This is the main source of levitation, which will be explained on later in the video by Heather and Zach. On the sides, we have Alnico magnets stuck on to center the levitation of the alloy box carrying the actual goggles. This box, as mentioned earlier, slots onto the pre-made robot, and external systems such as temporary mounting hinges and screws could be put in to help the box firm in its place. The final component is our magnesium alloy box, which holds the Sophie-like goggles and levitates on top of the maglev box. This box's measurements were made using anthropometric data to allow easy extraction and insertion of the goggles into the box. Now, on to Callum for all the tech info.
As you can see, we have decided to produce a CAD model using Inventor software to visualize our 3D model. Also, we have produced measurements and component pages to see how components would be put together. One of these components was a mobile component. We couldn't buy this for the actual robot, so we used what we had around. That was the LEGO EV3 robot. This one allowed us to mimic sensors that would be on the Agelux tracer, hence the sketch model closest possible to our end final solution. We are revisiting the code as it didn't work, and it will be ready for our final model. I would now like to hand over to Zach and Heather more about their maglev.
Our purpose was to show that the idea was feasible and to show a scaled down demo of the final mechanism. We began by understanding the physics behind maglev by using coils with current running through them. We found through further experimentation that different coils induce different magnitudes of magnetic field depending on the currents used. Our initial conclusion found that the 2,400 turn coil gave us a big magnetic field with a smaller current. The lab packs we have access to in school limited us with the amount of current that we could use.
To show an early activation of our idea in experiment form, we used one coil and a magnet to induce a lift. To this we added a stabilising wheeler contraption to prevent the magnet flipping and also to show the lift clearly. The difficulties faced with using this wheeler jig consisted of unstable holding with sellotape, unnecessary friction caused by angled sides, and only being able to lift one magnet and not knowing the actual load it could carry when put in practice.
Because this one didn't work, we solved this by creating a longer and more durable contraption using several rulers that had magnets taped below them. This allowed us to place a load on top and determine through calculations how strong the magnetic field that we induced were. This eliminated the limitations of using only one magnet, but it wasn't very durable and so it wasn't stable enough to stay above the coils unsupported. This was the developed contraption that we made.
We needed to think of a way that could eliminate/reduce these new and recurring issues, so we considered making a jig with several materials, such as wood, cardboard and cardboard. Our final decision though came down to acrylic due to its low friction and speed in production with a laser printer. We used 2D CAD/CAM software to design a shape that could be cut out using a laser printer. Assembled it to make our final encasing for our experiment as shown.
This encasement now provided us with both the stability and rigidity to withstand an approximate 2.2 kg gross weight and a 1 kg net weight. The restriction of our equipment prevented us from attempting more current, hence weight, with a maximum current output of 4.9 amps at room temperature. In industry, with installation of a cooling system, we could reach higher currents and therefore achieve a higher lift. This can be done with fans or with radiators and a liquid cooling system to maximise the thermal transfer.
We'll now show a demonstration of the lift.
The role of an engineering technician was a challenging task, with the end goal being to produce a practical 3D model. Our model had to be as close to the final product as possible while still fitting in within the boundaries of sketch model. After brainstorming a couple of ideas, we 3D printed our connecting bracket. This would attach a storage unit onto the LEGO 83 robot. In order to do this, we utilised our existing skills as a dental professional to design and develop our sketches.
With our parts created online, we utilised our 3D printing machine to create physical models using PLA polymer, a sustainable plastic which is biodegradable. However, creating our initial model was not a smooth process. A key difficulty that I faced during 3D printing was when our parts curled during the printing. As you can see here, the initial product was curving at the bottom due to a lack of support. However, after brainstorming and testing, we managed to produce a clean slate bottom. Once we had finished 3D printing our bracket, we then created a box out of Capaboard. This is going to attach on top of the robot, and it will hold the military thermal cameras. After our initial model was created, we headed to TALIS to gain some feedback.
After our meet, we regrouped as a team to discuss our next steps that have to be taken to ensure success. Our final draft had some changes, while the core idea stayed the same. A new process that we learned was laser cutting, which was used to create our outer shell. With the parts cut and ready, we used a lot of hot glue and care to create our final product.
Our Talic features a large white Capaboard body. The corners of our model have been curved to create a curved edge. Additionally, a clear acrylic dome has been attached to the top of the model to allow access to the storage space. This dome is detachable. Finally, the Talic is decorated in TALES and TIKOS branding to give our model a professional look.
Overall, our model has come out very successful, fitting with our provided criteria. So we hope you not only enjoyed our journey, but also gained some insight into how we handled, progressed on and concluded our project.
Thank you. We were TIKOS.
Well, I'm Callum and I was a graphic designer at Obviously we can buy the sorry.
As we embarked on our industrial cadets journey, we were set out.
As you can see, we have decided to produce our CAD model in Inventor to 3D solution. Also, we have
Which was viewed up whatever ideas came to mind, approaching this with the mindset that no idea was a bad idea. So as you can imagine, we got some crazy ones. Taking the general gist of these ideas, we needed a...
Now do a demonstration of how it works.
We'll now demonstrate it back to you.
Oh, let's redo that.
PE